All right, and yeah, so today we're going to just talk about like section 28. So really this is kind of like building up from like 25, 26, 27, really 26 and 27 and kind of building up saying like, how we can kind of improve further and further. The linear algebra aspect will be important as we kind of do gradient descent, but we're kind of going back a little bit back to linear regression and saying, like, what can we improve, right? Like, I think I mentioned this like plenty of times, right? It's like, I kind of like warn you guys, like this is not like the end of the model, right? Like there's so much more you can do with linear regression. And so we talked about obviously multiple linear regression, so like multiple features, right? And so what this first half of the section really talks about is saying, well, okay, like, we have this linear regression, multiple linear regression. How do we improve it? And there's a bunch of there's a couple things we can do. So I'm going to share my screen and we'll talk about those two. Here we go. Is that right? Yeah. Okay. And of course, I was just talking to someone about my Zoom settings. I'm like, I got to figure out why my window gets put behind the other one, but that's okay. All right. So the first basically like thing we can do is the curriculum talks about is interactions. So I kind of talked about this a little bit before, I think, like if you remember back in module 1 is saying, sometimes like you can't actually predict well off of like a linear fashion. Because remember, the whole point of like linear regression is that we're using linear, lines, like we're using lines to predict these factors. So the thing is that interactions might have something where the variables interact together that cause an effect that is different from the sum of their parts. So you kind of imagine this as being like the simple example of like non-interacting features, which is what we assumed before, is that if you have a bigger house, for example, and like you're trying to predict sales price, like if the square footage goes up, the price of the home goes up. And if you have more bedrooms, the price of the home also goes up. So if you have a bigger house with more bedrooms, you'll have a larger sales price than a house with a smaller house with a low number of bedrooms, right? But maybe that's not actually true. Maybe that's kind of like, you can imagine maybe a scenario where like if you have a small house in many bedrooms, like they sectioned off every like little corner of the house into like a bedroom where each bedroom's like 50 square feet, like that probably would not sell very well, right? So you can imagine that maybe these things are not actually additive, where a small house with more bedrooms might actually cost less than a small house with few bedrooms, and where a big house with more bedrooms might actually, cost more than a big house with a few number of bedrooms. So you can kind of see like there's kind of this, it depends, like basically they're dependent on each other. They're interacting in that way. And that's what we talk about with being there's an effect stronger than some of their parts. So this was an example kind of shown like in the curriculum where there's basically diet in the country. And so you can see here, like this is like the weight change and there's diet A, B, and C. And that for the most part, it's like, oh, like, we can see from USA to UK is that essentially diet C is better in weight change, I guess. I'm assuming weight change is what they want to have. So diet C is better than diet A, than diet B, and that's consistent for USA and the UK. However, if we look at something like New Zealand, if we were expecting the same thing, like, we might have like the green, like right over here, like where the legend is. But instead what we see is that actually diet A is the best diet and diet C and B don't really matter. So there seems to be some interaction, like if, that maybe it depends on the country and what diet you pick. And this could be something like, a whole bunch of examples. You can imagine that maybe it's dealing with the fact that like New Zealand like has a like doesn't really like diet C, or like can't stick to diet C very well for whatever cultural reasons, or whatever available for food, like whatever's like in there. If you imagine probably in like, I don't know, in the US, like if we said, oh, getting rid of cheese, cheese is probably really common in the US by itself. So like, if you ever notice, like on like any, like, for example, any fast food menu, there's always like cheese. I think there's even like, if you ask for like a burger, they usually say, do you want cheese with that or something like that? So you can imagine certain things like this. So that's kind of the idea of like this confounding factor, where basically there's something that's interacting beyond just saying, oh, it's just essentially diet C, diet B, or diet C, diet A, and diet B. So that's kind of an example here. So the curriculum kind of goes into more of the code. I won't go through it all, but because it's in the curriculum. But this is the graph that's produced from there, and they basically are looking at something. I think it was horsepower, and then miles per gallon was basically their target, right? Starting to predict miles per gallon. And the origin, which I think ended up being like the origin of manufacture. I don't remember actually what the origin was. That right?
I think it's, yeah, the manufacturers fall into North America, Europe, and Asia
Okay.
categories.
And that was represented by origin, is that right?
Yeah, I think so.
Yeah, okay. So that's what we'll go off of, right? So this is like the different, like, you know, place it was like manufactured, right? Origin 1, origin 2, origin 3. And you can see here is like based on the origin, which are different colors. We have the blue one here, the red one, and the yellow one. And we have the horsepower. And essentially, as horsepower increases, miles per gallon goes down. And you can see that if we looked at basically the linear regression line for just origin 2, just origin 3, and then origin 1, they more or less are about parallel with each other. And that kind of suggests like kind of similar to like the US UK. Essentially, we can just simply shift them up and down. So you can imagine the different categories that we talked about before. This is what would be a category, right? Is essentially we just shift it up by a certain amount from like, let's say origin 1 is our main category. We shift it up a certain amount and shift origin 3 a certain amount. So this is perfectly fine. This would work good with our normal multiple linear regression that we've done before. Then they kind of talk about saying, well, let's see an interacting feature. And what they show here is a difference between younger cars and older cars. So you can see younger cars in red here going in this direction with its little line just focusing on just the red, and the older cars in blue compared to horsepower. And you can see here is that it's not as simple as saying, oh, if you're an older car or if you're an older car, you have lower mile per gallon. It's definitely a crossover here. And it seems to say that basically they don't have the same slope. So there's an interaction in the sense of being older or younger with the horsepower. Essentially, it looks like maybe older cars were slightly more efficient with higher horsepower than newer cars with that same horsepower over here. So what that might say is like, okay, like that means it's a different kind of feature. So the way you can visually see this is that it's not a parallel slope, essentially, that interaction here. So the way we can kind of deal with this, actually, did I get rid of this part? Sorry, kind of talking to myself a little bit. I think I moved this thing in the wrong place. Okay, I'll just verbally kind of talk about this through. I thought I had this in here. That's what's throwing me off. Anyway, but what we can think of this then is essentially, like if you remember back to doing linear regression, you can look at this equation down here, right? So we'll talk about polynomial in a second. But if you think of like this equation, we essentially have a weight. So that's kind of like our y-intercept, right? We just have like our intercept. But then everything else we have essentially is our feature, x1, right? And then a weight, w1, right? And then a feature x2, and then its weight, its coefficient w2. So we'd have this for each individual feature. And this assumed that basically there was no interaction. But since these two interact, what we can have is like a new feature. And we'll call this like, I'll call it like wn plus 1. And so remember, we only have like n features, but let's say it was like, oh, we want to talk about these parts interacting. What we can do is like, okay, well, there's this new feature, and we'll just call it right now x n plus 1. So now we have an additional feature. And what this feature actually is, like if I were to set this equal to, is let's say this is older cars, younger cars is like x1, and let's say horsepower is x2. So that's the different features. This is going to represent x1 times x2. And so the idea here is that they're combining in some form or fashion. They're interacting with each other. So this basically creates a new kind of feature. You kind of treat this as like a new xn plus 1. And this will have its own coefficient by itself. And what's kind of cool is that you can basically just do the same exact thing, except just make essentially, like if you want to do this in pandas, you can essentially just make a new column using these interacting features and then run your linear regression just like you normally did. But just remember in the back of your mind, like, oh, like this is a combination of horsepower and the age of the car. So you might have like horsepower underscore age interaction or something like that. And that way you can see like how well does it perform. And if you treat this as its own separate interaction or own separate feature, you can say, oh, this feature, like you just looking at your outputs, you say, oh, this feature has a low p-value. This has a better value in r, basically increases the r squared value relatively well, or just at r squared value. So you can actually use, say, hey, this is pretty good. And this is where like the next question you might ask is like, well, how do I know which one to check for interactions, right? Because you imagine you have like 10 or 20 or however many features you have. Obviously, this would be really difficult to go through. And the short answer is there's two ways to do it. In one way is basically just have all the features interacting. But what might be the issue with, you can already probably tell like that's not a good idea, but like what happens if you include every single interaction that you possibly can have? What might be an issue with when you try to do the linear regression then?
That's a lot of features.
Yeah.
And what if then you start getting interactions between the interactions? I mean, it's just
Yes. Yes, and you can get interactions with interactions, right? So one's a lot of features, right? So you imagine like all the different combinations you can make up. There's 10 features, right? That's x1 and x2, x1 and x3, x1 and x4, and then x2 and x3, x3 and x4, and so on, right? You can see it's going to be pretty big. It goes up to factorial like. So the problem is like you're going to have a lot of features. So one, you're going to have a lot of features, a lot of things to put in your computer. It's going to take a long time. But two, also having a lot of features, as we already know in the past, is not really the best thing to do, right? We can bump our R-squared value, but it's going to keep our adjusted R-squared value lower because essentially we're having too many features and stuff like that. So a better way to do it is basically saying, well, okay, what things, especially from domain knowledge of saying like, what things would have an interaction between the two? And you might have to kind of look at that, and then you can see these little graphs of like actually plotting out these plots and say, okay, like, well, let me check out like horsepower versus origin, or, you know, it's like, I think that might have a difference. And you look at it like, oh, it looks like there's not really much of an interaction in there. Another thing is like, oh, let me try horsepower in this feature, horsepower in this feature, and like things that like you would think would have an interaction. The downside of this, obviously, is that you might miss an important interaction that doesn't exist. So you might also basically try a simple linear regression with all the features with no interactions and see which things didn't perform very well. And this is where, for example, we do our correlation graph, and if we notice our data set doesn't look very linear, if you see something that looks, like our data points that kind of go up like this, that might suggest like, hey, there's something going on right here. Like what would be kind of creating this kind of extra part, and see if we can treat that with an interaction. Maybe you can reason that out. So obviously this is where you can tell this can take a long time, like, because you essentially have to decide what thing works really well. There's not like a real good automated way to do this, right? So that's kind of like what you'd have to do for your interaction. But you could technically put as many interactions as you want, but you put in the danger of having too many features. Cool. Make sense so far? Any questions on that interaction or how that comes into play? No?
I have a question.
Yeah.
Like I get it, but like I understand the process, but why do you multiply the features together?
That's a good point, right? So the idea here is that like there's some kind of combination that they are, how do I say this? In mathematics, you can kind of imagine like when the way we're treating our linear regression is being addition, right? And that's basically saying like they're independent from each other. By multiplying them together, basically what you're saying is like, well, there's some kind of combination between these two that are affecting, let's say, that can be like adjusted with just this one coefficient. So that's kind of like my kind of quick hand wavy, like it's mathematics, like multiplication kind of implies, interaction. But another way you can think of this too is like if you imagine, let's say we have, instead of categories, I kind of like doing this with, I'm gonna clear this out and just try to draw a little bit on the side here. But you can imagine like having something like I said, let's say housing size, so let's say square foot. And I'm gonna just put on a plot against here, right? Square footage and number of bedrooms. Okay. And so the target is gonna be like sales price, but we're not plotting this right now. And you can imagine like as square footage for number of bedrooms, if you have a high number of, what's it called? You have a high number of bedrooms, this is gonna be a low price. So with low square footage, and this is gonna be a better price. And this is going to be a low price right here. And it's going to be a better price right here. And so essentially what this means, like, oh, we have a line in here that's representative of this. And essentially you can treat this whole line by itself as interacting part. So like imagine like a low number here. Essentially if you have a low number here, so let's take this close to 0 and this is close to 1. Okay, 1 times 0 is going to be 0, right? And then if you have something over here, we have a low number, a high number here, and a high number here. Well, this one's going to be a low times a high, which is also going to be 0. So hopefully this isn't getting too messy. I'm trying to do my best to keep it together. But you can imagine this x here is going to sum close to 0, and this one over here is going to be, I'm sorry, not sum, but it's going to be multiplied close to 0, and this number here will be close to 0, versus these numbers will be relatively small, but they'll increase in this direction. So the idea here is if you multiply them together, you would get this kind of like pattern right here, and that would relate to the target itself.
Okay, I get it. Kind of filters out the values that you don't want so much.
Yeah, essentially you're kind of like the extreme ends would not be very good. So if it has a low number to begin with, it should drop everything else down. So that's why, that's the kind of like the instinct of like why you would use multiplication.
Okay.
Yeah. Now this kind of goes into a little bit of saying like, well, why do we have to just multiply them? Could we just do like, for example, let's say we have something like x1 squared times x2. And like you can technically see like maybe there's a more complex pattern within that. Like I showed like that x and like that. Maybe it looks more like this or something like that, like some parabola kind of deal. It's like, well, then that means you might actually have to have higher denominations here. It's like, okay, that, and you can get these really complicated parts. And that's what leads us into polynomial regression. So essentially what polynomial regression allows us to do is to say, well, okay, like this feature by itself, let's say, for example, like horsepower or something like that. And it looks kind of closer to like this versus like a linear line. Okay, against the target, right? And so this is suggestive, like, well, this really isn't a line. We'll never get a line that's going to make it fit, right? We really should get a nice line or a model that's going to fit along this curve, which suggests probably like something like x1 squared, right? And that's where polynomial regression kind of comes in. So just kind of show this a little bit. These are also from the curriculum. So you can kind of see here in this case, they have an example of yield versus temperature. I can't remember the exact data set, but again, it's just basically just random data. And you can see a line will never fit through this perfectly, right? Like you can never draw a straight line that's ever going to perfectly fit through this. So one thing you can do is like, well, let's go ahead and make it a polynomial. So one, it's like, oh, this looks like an x squared thing, but you can also think of it, if you guys remember back from like, I don't know, maybe like high school, we talk about like the degree of a polynomial and stuff like that. We can say like, you know, y equals like, you know, I won't write the coefficients, but like x, or we can do plus x squared, right? So this would describe a parabola, right? Some form of parabola. And you could simplify this to whatever form, but it would be some parabola, and this would be a cubic function, and you can go up as many high degrees as you want. So the idea here is like we can basically keep adding like degrees or different, that's not the right word for it, but basically we can have different features raised to different powers added up together to make a higher degree polynomial for that one feature. So kind of like showing right here, you can see here what's going on. It's essentially linear regression again. The only difference is that now instead of having, you know, just x1, x2, all that stuff, we can now use higher powers. So this essentially, you can imagine this being like, okay, this is like my x1 thing. This x squared part could be like my second feature, and this could be like, for example, my xn feature. Okay, so essentially what we're doing is saying almost in a lot of ways, you can think of it as like interaction with itself. But really what it's saying, like, oh, we're just making this like x squared, this x1 squared feature as like its new feature, x2. Okay. So note that again, we can kind of extend however far we want, right? We can have as many powers. So we have these two differences right here. So you can see here, like, oh, this looks pretty good, right? Like pretty decently, but look at this one. This one's really good, right? It fits really, really well. Okay. So one thing to note though is like, which of these two would you actually say is quote unquote a better model for this data set? And if you can give an explanation why.
I would say the parabolic one, probably the x squared, just because it looks more robust than like the bottom one, which is gonna looks like it's might be trying to overfit. Like it will work on that data set, but maybe not what you pass in next time.
Yeah, good point, right? So this is something we'll go into next, right? Is that this probably will be a better model overall because there's data we haven't seen yet. Like think of like the test set, right? Like you said, Andy, is that it might have data that it hasn't seen yet. And maybe this is just like, for example, this one kind of bumps up a little bit, but maybe that's just a random fluctuation. Maybe it really is much closer to like the true pattern. It looks like this. So if we basically add this part in here, well, that's going to miss the true pattern that looks like this. It's basically being too precise. It's looking at all that extra noise and being careful with it, or not being careful with it, being like saying, oh, this extra noise is a meaningful result. So this is where, for example, you want to, if you're doing polynomial regression, you want to keep as low as possible your polynomial. That way you don't, the degree of the polynomial, that way you don't have these extra features or these extra little curves and stuff like this within your model. Okay, So something to kind of keep in mind. But again, you could technically do this for each individual feature. So you can imagine if you have multiple variables, you can see here, like we have x1 feature, x2 feature, x3 feature, and each one of these can have their own degree of polynomial, right? So you can have x1 squared, x1 cubed, or x2 squared, x2 cubed, and so on. So if you wrote this mathematically, this is what it might look like. Okay, so cool. So kind of like a little kind of things to kind of think about. We don't have to discuss this out loud necessarily, but note that there's no degree, like there's no limit to the polynomial degree. We could put this out to like, 100 polynomial, like for each one. And imagine you could have 10 features with 100 polynomial, right? Without ever interacting features by themselves. So we didn't even talk about interacting features, but you note that we can find polynomial and interacting features together. But just this part, you can say, oh, 10 features and 100 different, degrees. That's going to be what, 1,000 different, features. Obviously, R squared here is not going to do too well. I mean, R squared is going to do better, but your adjusted R squared is probably not going to do as well, right? And you don't want to get into this overfitting, is what we'll call it. That's when we try to fit too well to the training data. And essentially, higher degree polynomials, the more complicated the model is, the more it'll try to fit in these little new little extra parts and everything like that. Okay, cool. Yeah. So do you guys have any questions overall for like how this interacting or polynomial like regression can be useful, or when it's appropriate? Okay, yeah. And the main idea here is that, just kind of emphasizes that if our model's more complicated like this, right, a linear line will never go through it. So we essentially use polynomial or interacting features essentially to try to build up, a more complicated model. But we don't want to get too complicated, or else we get into this kind of area of overfitting.